8.78 is a fairly complicated problem. So in this, you have something they call the tray, or sorry, they call it a frame. I'm going to think of it more as a tray. A bit of putty. So putty, one of the principal properties of putty is that it's deformable and mashable and mushable and stringy and gummy. So it's going to get dropped onto the tray and then stick. And then we have the spring. It's got some equilibrium length. It's hanging from the ceiling. When you attach the frame or the tray onto the end of the spring, it's going to elongate the spring a little bit, and I'm going to follow the textbook numbers and use the elongation of 0.04 meters. I'm also going to give it a name because I don't want to write 0.04 all the time. I'll just call that D. So D is the elongation length of the spring just when you attach that frame. The frame has a mass, well, let's see. I want to do this cleanly. Alright. The frame has a mass, I'll call it capital M, and that mass is 1.5 kilograms. 0.150 kilograms. That putty has a mass, and I'm going to give it the label little m, and it will be 0.20 kilograms. Make sure I got that number right. Yep. Okay, so first we start with the pieces. This is all the pieces of the problem. You hang that frame onto the spring. It stretches the spring out by 0.04. Get rid of that. It's just in the way. Come on. Okay, then the putty appears. And what happens here is we're going to hold that putty up a distance h, which is 0.3 meters above the frame, and we're going to drop it. That thing falls down, it gains speed, it hits the bottom, and then it pulls the spring down with it. That spring will eventually stop, and then it comes back up, and ignore this one. We want to know, so this picture is just before or right when the putty hits the frame, and it hasn't moved yet. So nothing's moved. I mean, the putty's moved, I guess, but the frame hasn't moved yet. So what the question we're asked is, what is this displacement of the spring? How do they word it? What is the maximum distance the frame moves downward from its initial equilibrium position? The frame, right? So here's the frame's equilibrium position. And then once the putty hits it and drags everything down, that's the maximum distance. Because everything will shoot back up after this point. So we are looking for this, what I'll call delta y. I'm going to get rid of these arrowheads. Okay, so what's the plan? We'll probably need the spring constant, and we can get that from this picture. We can get the spring constant from the clues here. We can get the speed of the putty from this this info. Speed of the putty just before it hits the frame. Maybe I should fix that. This info gives us the speed of the putty just before it hits the frame, whatever that really means. And here we're looking for the delta y. Well, how do we do that? If we could find the speed of the frame plus putty of frame plus putty, so that combination, then we can use energy conservation to find the delta y. Increase to make that clear. Okay, so by the way, we can use energy conservation here. So conservation of energy here, conservation of energy here. Here we're going to use balance. Here, what should I call it? Force balance, maybe? Force balance. So that concept there. Conservation of energy. Conservation of energy. Get rid of this. But in between, let me label these. Let's say this is state 0, I guess, state 1, state 2, state 3, and then here they were just the pieces of the problem. Why is that so thin? So between states 1 and 2, actually, no, I mean, there's actually, okay, at state 2, there's kind of... What's happening? Sorry guys, I didn't have much time to think about how to explain this. Let's say that just before the putty hits the frame, just after or till just after maybe. So we can use conservation of momentum for a very brief moment, just to figure out the speed of the frame and putty object. Now this is bugging me. So after the collision, the frame and putty become one object, because it's a totally inelastic collision. We can use the conservation of momentum just for a brief moment, or maybe like 2 moments. We can compare the momentum of the system just before the putty hits the frame to the momentum just after the putty hits the frame. It's a, like, you know, another problem is we say momentum is not conserved. Well, in general, it's not. Even in this problem, the momentum isn't conserved throughout the whole time. And that's usually what we mean when we say the momentum is not conserved. But, and gravity's accelerating the putty downwards, right? So the putty's momentum isn't conserved. It started off as 0 because we just let it go. It gains momentum as it goes down. But if for a moment we just ignored everything that happened to the putty before it hit and just paid attention to right before it hits, so it's got some velocity, hits the frame, sticks to the frame, and then the frame putty object has a velocity, you can conserve momentum for just that brief interval, just to figure out the speed, and then go back into energy conservation. Okay, so that's the plan. Where should we start, though? You know, honestly, I think starting at the end will be the best thing to do. So, I don't know how to spell. Suppose the frame plus putty, the putty plus frame object with mass m equals little m plus big M, because I don't want to keep writing little m plus big M, so I'll just do m with a bar over it. So we're going to assume that V, big V, I'll just call it big V, okay, so suppose we know, let me keep going, has a velocity V just after the putty sticks to the frame. Then what do? Well, then it's basically the energy of state 2 will equal the energy of state 3. And the energy of state 2, well, what's got energy? So the frame putty object has a kinetic energy, 1/2 the combined mass times its velocity squared, plus okay, so there is kinetic energy, or there is potential energy in that spring. So remember, we've stretched the spring a little bit, a distance d. So there's spring potential energy here, 1/2 k d squared. We don't know k yet, but we can figure it out, don't worry about it. So that kinetic energy is here, or sorry, that potential energy is in the spring there, since nothing's changed about the spring yet in this case. That potential energy is still there. Here the putties hit the frame. Yeah, let's say state 2 is just after the putties hit the frame. But immediately after. There's been no stretch here yet. So that spring potential energy is still 1/2 kd squared. Here though, it's 1/2 k d plus delta y squared. So this you know what, I'll call this is just the energy E1, no, E0. And so in state 0, it's just got a spring potential energy, E0. So that E0 is present here, here. But here, the spring potential energy don't want to confuse anyone. Yeah, let me just keep going. So the energy in state 2, I'm going to add that spring potential energy. So this system is moving with the velocity capital V. We've got the kinetic, or the potential energy here. What else do we have? We actually have some gravitational potential energy. Man. Come on. Okay, this, I could put it like here too. If that helps. And set this line to be y equals 0. So when the combined mass is delta y above, it's going to have a potential energy of mg delta y versus the gravitational potential energy here will be mg times 0. So I'll just drag that down here. So here is the total mechanical energy of state 2. What about state 3? In state 3, we're at y equals 0, so no gravitational potential. Everything is stopped, so there's no speed, there's no kinetic energy. So these two are 0. And all the energy is in the spring potential energy. 1/2 k. But the stretch, it's d plus delta y squared. And now, when you set these two equal to each other, because energy is conserved, and we're looking for delta y, we can solve for delta y. It's going to be a quadratic equation because of this term here. But let's just equate them. And I'm going to expand this term. So that's d squared plus delta y squared plus 2d delta y. And we have some common terms, or at least one common term. Those two terms will cancel from both sides. That's pretty much the only big help we get. So after canceling that, we have k d delta y. And now I'm going to divide both sides by k, which I still don't know yet. I can figure it out, but I want to basically get the answer and then figure out what I need to actually get the number. So when I divide by k, on the right side I'm left with delta y squared. I'm trying to sort of isolate the delta y squared so that I can make the negative b plus or minus b squared minus 4ac thing all over 2a easier to calculate. And so I want to leave the 1/2 because that'll be the a coefficient. So cancel out the k's on this side, and then on this side m bar over 2k capital V squared plus m bar g over k delta y. And I'll take this term and combine it with this term, throwing it over this way. So I want to keep the plus 1/2 coefficient in front of that delta y squared. So, and then I'll subtract this term to the other over to the other side. So I get a 0 equals delta y squared over 2 plus d minus m bar g over k delta y minus m bar for 2k times v squared. So d is given, m bar is basically given, g I know, k I can figure out really easily. The only thing I don't quite know yet is capital V, and I'm looking for delta y. Alright, I need a new page, and that was the last result from the previous page. This program, I hate it. Alright, so again, I'm trying to solve for delta y squared. This is a quadratic formula, or a quadratic equation, so I'm going to use the quadratic formula. Negative b, this whole term is b. Negative b plus or minus square root b squared minus 4, a is 1/2, c is negative m bar capital V squared over 2k. And it's over 2a, right? Everything's over 2a, but a is just 1/2, and so everything's over 1. That's why I left the 1/2 there, so I don't need to worry about that stuff. And I'll just clean this up a tiny bit. Mainly inside the radical, the square root sign, or the square root. When I actually calculate the number, this d minus m bar g over k, I think I'll just do that once, and then I'll have both of those. There's 2 negative signs, so it becomes positive here. And then I got 2 2's on the bottom, so that's a 4 on the bottom and then a 4 on the top. So all I have really is m bar v squared over k. All right. Let me calculate what k is real quick, and then we'll get to what capital V is. So we get k from information of state 1 or state 0. How is that? Well, look at the force diagram. The spring force pulling up on the frame, going upwards, and then the frame's weight downwards. So that's capital M times G. Has to be balanced with the spring force, whose magnitude is K times D. So K will be equal to mg, capital MG, over D. We'll go back down here. Paste that result. We could put it in. Should we put it in? I don't think it'll really help. So let's not. Let's just calculate the number. So big M was 0.15. It's 9.8. And D was what was it? 0.04. .75 newtons per meter. So with that, we can basically plug all of these numbers in and get those. So should we do that? Maybe we should do that. Change to black. So delta y is equal to negative 0.04 minus little m was 0.2, big M was 0.15, so that's 0.35. 9.8 divided by 36.75. Actually, let me just calculate what that is, even without the negative sign, because then I'll just put it into these guys. So I'll start here, 0.35 times 9.8 divided by 36.75. Negate that and add it to 0.04. So I get this to be negative 5.33333, so on, times 10 to the minus 2. I'm going to save that. So delta y is equal to 5.3333 times 10 to the minus 2 plus or minus square of that, 2.8444 times 10 to the minus 3 plus 0.35 divided by 36.75, 9.5238 times 10 to the minus 3, that's a 3, times capital V squared, which we don't know yet. But otherwise, we would have the answer here. Okay, so how do we get big V, which is the velocity of the frame plus putty object just after they collide, or just after the putty lands on it? Let's go back to the picture. So from state 1, the putty is going to gain speed, land on the frame, what's the speed that the putty lands with? Well, we'll just take the transfer of kinetic energy, mgh, and set that equal to the kinetic energy gain. That's a square. V squared is equal to 2gh. V, little v is square root of 2gh. Okay, so that's the velocity with which the putty hits the frame. So the momentum the putty has is little m times v, and we're going to set that equal to the combined system's momentum, the combined thing's momentum. And this will be true for just a moment. Alright. But that's all we need. So now that velocity m little v over the combined mass is so 0.2 divided by 0.35 times square root of 2 times 9.8 times 0.3. .8 times 2 times 0.3. Take the square root of that times 0.2 divided by 0.35. Looks like the velocity is 1.3856 meters per second. So I'll just copy that, go to the next page. Now we got another bit of information. That's the last bit of information, actually. So take the square of that times 9.5238 e to the negative 3 plus 2.84444 times 10 to the minus 3. Take the square root of that. So it looks like delta y (5.333), etc. 10 to the minus 2 plus or minus 1.4536 times 10 to the minus 1. Save. Let's see, how do I want to do this? I'll store that. 5.3333 e to the times 10 to the minus 2 plus no. Hold on. That plus alright, I'm just going to type it. Trying to be clever with my memory features, but it's not working. 1.4536 10 1. I get 1.9869 times 10 to the minus 1 meters and 5.333 times 10 to the minus 2 minus 1.4536 10 to the minus 1, negative 9.203 10 to the minus 2 meters. The way we did the problem, delta y has to have been it needs to be negative, or it needs to be positive. So forget about that. Here we go. Here's the answer. That was a lot of work, actually.